All right, welcome to my session for the Granite State Code Camp. So thank you for coming out today. My name is Richard Crane. I am the founder and CTO of Mill5. Today I'm here to talk about advanced microservices with .NET 7. I can't see people that are on the chat or on the virtual session, but for the people that are in the room, how many people are using .NET right now? Yes, no? No, no, no. Okay, well, this will be eye-opening. All right. So 2 seconds about Mill5. We're a global technology company. We primarily focus on technology consulting, and we do build product as well. We are composed of some world-class technologists. And we were formed, 7 years ago? And we're now over 100 people. We're actually approaching that 130 mark at this moment in time. So. Our core services, software consulting, performance engineering, and managed services. So we offer all three of those things. Solutions, anything cool, we pretty much do. AI, machine learning, data, cloud, a lot of IoT, a ton of IoT, a lot of modern applications. We're not industry specific, but we do tend to focus on three main things, which is financial services, healthcare, and then we lump a couple others like manufacturing, power, and utilities into the same group because they have sort of the same problems. I mentioned on the previous slide, we grew, and we grew big time. So we have an office in the United States in Boston, one in Medellin, Colombia, one in Buenos Aires, Argentina, and one in Hyderabad, India. So we've been on a mission and we continue to grow. So hopefully next year you'll see more offices on the list. 2 seconds about me. I already mentioned I'm founder CTO of Mill5. I worked at Microsoft for 10 years, just a little company. They do some things that you might know, like Azure and .NET and stuff like that. Along the way, I got my master's in SQL Server. So this is a special certification for people. You have to spend 5 weeks, you have to pass these grueling tests, and you have to do all these labs. And I was one of the few people that passed. So out of the 25 in my class, 3 people passed first time through, and I was one. I love software, but my degree is not in software. My degree is in electrical and computer engineering. I graduated from Drexel University with summa cum laude, and I'm actually a former professor from Drexel. I wrote a book, little technology called Windows Communication Foundation. It is somewhat relevant to today's talk. And I wrote an article for SD Times on how to develop high quality code the .NET way. Bob German, who is another speaker at this session, he's actually same time as me right now, so he's not in the audience. We were kind of bummed out. He's the one that actually prompted me to write that last article. So, all right. Just 2 seconds. All of these names I have done work for and actually have code actively in their products right now. So everything from NASDAQ to Olympus to Wayfair to MATLAB, Emerson with PlantWeb, SQL Server, Windows, right? So it's very, very cool. I can honestly say I love what I do, and this shows. Okay, how many of you have heard of microservices? Raise your hands. You haven't heard of microservices. Okay. Microservices. Well, people have heard of APIs, application programming interfaces. People have heard of things like web services. Microservices is kind of a special category of those type of services. They're independent services. They often focus on a certain feature or function. They're often isolated. Most modern applications today are built using microservices. So before, when you built applications in the past, you built this big monolith application and all the functionality was in it. Well, that had some challenges. One of the challenges was, hey, I need to update the thing. And when I go and update it, it's hard, right? Because there's all this functionality in there. Another reason why monolithic applications are hard is it's hard to scale them, right? You go deploy one instance of it, and you have to deploy many instances of it, and you're deploying everything, right? Not one thing, everything. So as your application becomes more and more in production and used by your users, deployment starts to become an issue. And then there's performance. So if you have your application performing everything, quite frankly, has to do everything, and therefore everything needs to perform, but we don't have unlimited server resources, unlimited compute power. So we often look at things and say, how can I break this apart so that I can scale just this one function or this one feature? Something I wanted to highlight here is kind of an interesting thing. I've had the opportunity to build applications for the last 30 years. And if you're in computer science and looking to get a job in today's modern computer science software world, and you want to get a job at somebody like Google or Amazon or Meta, even Fidelity or Apple, microservices is the backbone of most of what's happening behind the scenes, right? So they don't have just this one big application. They have many, many microservices, and applications become a collection of these microservices. So it does promote things like reusability, which is kind of cool, but it also promotes all the things I mentioned before: maintenance, scalability, performance, all that stuff. All right, challenges. We're no longer this one big application, this monolith. There's some nice things about a monolith. If I were to call a piece of function within my application, it's right there. It's in my process space. It's in my application. It's not in another process. It's not on another machine. So from a performance perspective, guess what? It's easy. It's fast. But one of the challenges when you start to remote your functionality, meaning go cross-process or go even in Kubernetes, like cross-pod or cross-container or cross-machine. Anytime you have a boundary, you might as well just say divide by 10. So if you did 1,000 things in process, you went cross-process, now you do 100 things. You go cross-machine, take another 10, right? So now you might be able to do 10 things. Why? Because you are traversing network boundaries. Traversing a network boundary is non-trivial. You lose performance and scalability, but you can get it back. And that's one of the purposes of this talk. The other thing that's interesting is application behavior. So before, you might have been doing things transactionally, say with a database, and things were easy. You have all these operations you need to do together, and you say, hey, start a transaction, do them against the database, end transaction, you're good. Well, now you might have to do that across many, many services. And what you're going to find is when you have to deal with things like transactional consistency across service boundaries, it's difficult. It's hard. And you have to change the behavior of your application to do things like eventual consistency, right? So rather than things being immediate, maybe things can be delayed. And therefore, if it's delayed, you're okay with that. But as long as it eventually gets consistent, you're fine. So these are just some of the things that happen when you move to a microservice application. Just curious, Jim, that binging, what is that?
That's people coming.
Okay. All right. So let's talk about service technologies. So I mentioned I've been doing some of this for some time. I've actually worked with every single one of these technologies. You may not know all these technologies, nor do you need to really fully understand some of these things, but just know that service-based technologies have changed greatly over the years. The oldest on this slide is Corba and message-based technology, and messaging is still used today. But as you progress forward on the .NET stack, you got things like COM Plus, Microsoft Transaction Server, .NET Remoting. Then you start getting into probably what's still used today, which is WSI Basic Profile Web Services. This is the core web service standard that's been around since the early to mid 2000s. This is stuff where they took HTTP and XML and said, hey, we can call a service. Then roll forward, they said, well, that's not good enough. And they came out with something, Microsoft came out with something called Windows Communication Foundation. And WCF tried to be all things to all people. Interestingly, there is a port of WCF to bring it to the latest .NET. So you can actually use WCF today, and it is a great technology. People still use it. It is a little difficult because there's a lot to it. There's a great book. I think I know one of the authors, namely me, who wrote Essential Windows Communication Foundation. So if you want to know more about WCF, definitely feel free to get the book. There's mine and a couple other books out there that are great. But roll forward. People thought WCF and WSI Basic Profile Web Services were kind of either complex or not good enough. In the case of traditional web services, it used XML. And they said, you know what, XML is a little bloated. We don't like that. It's very verbose. In the case of WCF, they said, oh, it's so complex, right? I don't need that complexity. Enter something called RESTful services. What this is the ability to create services using the HTTP standard, right? So that's the protocol that every browser uses out there. And then a serialization format, not XML, but something known as JSON, JavaScript Object Notation. Why JSON? Easy. How many browsers are on everybody's desktop around the planet? At least one, right? And usually 2 or 3, right? So you either have Edge or Chrome or Firefox or some other browser, and they all support JSON. Why? Because they all support JavaScript. So if you were to build a web-based application and you wanted to communicate to some service, either in the cloud or someplace else, REST kind of is your thing. So it's easy to do, and quite frankly, it fits the standards. The other reason to use JSON is because of all these browsers out there, you can be guaranteed that if you write an application, that your application will be able to get to many other people. So, all right, roll forward a little bit in time. There are some new standards. So we still love REST for all the reasons I just mentioned, but Google came out with gRPC. That stands for Google Remote Procedure Call. Why something else? Well, even though REST is ubiquitous, easy to get to, easy to consume, performance isn't always the best thing. Why? Because the HTTP protocol isn't the most performant protocol, right? It's built on top of TCP. It is, for the most part, a text-based protocol. And JSON is a text-based serialization format. So you're sending large amounts of data around, and that doesn't always perform well. All right, so last year I did a variation of this talk, and I was able to say 2018 onwards, RESTful services plus gRPC services. This year, I'm able to say the same thing, but add one new thing, HTTP 3.0. So we talk about the HTTP protocol standard. There's been many versions of that standard over the years. Started with 1.0, then went to 1.1, then 2.0, and now we're on 3.0. There have been various features along the way. HTTP 3 is a game changer. So if you're going to build services, highly recommend that you start looking at how you can adopt HTTP 3. It's not going to be easy. I'll talk about that. But if you get ahead of the game, you'll be better off. All right. So I wanted to talk about advanced microservices. To build advanced microservices, you have to know what are the patterns and practices that you should think about when building these services. The very first one is one that goes back through all the years that I mentioned on the services slide. Be chunky, not chatty. So what does this mean? You build a service and you're requesting information, build it in such a way that you can make a single request and get all the information you want back. Sometimes that's not possible. Sometimes it makes sense to break it up. But if you're saying, hey, I want to get person's information and their address, well, you can model that in 2 calls. Or you can say, hey, just get person details and make a single call, which gets that person and the address information back at the same time. One of the challenges with some of the older service technologies, I'm thinking very specifically of .NET remoting, they tended to be more object-based, where you have an object, say a person object, and that object has details like first name, last name, and then you might have a collection of addresses, like your home address, your work address, and things like that. Well, in that style of object-based services, it was common to say, hey, let me get the first name, let me get the last name, let me get the addresses, right? And, addresses could be get all addresses or get one at a time. That ended up being multiple calls across the wire. Anytime you traverse a network boundary, it causes a scalability and performance impact. Now, I mentioned you can get some of this back. Yes, you can. You can scale out. You can scale up. But that costs you more money because you're investing in hardware and infrastructure. But those things might get you throughput, scalability. They may not get you performance. Meaning, if I have a single application that needs all that information, I still have to make the multiple calls and get it back. So you might have reclaimed performance, but you did not reclaim, you may have reclaimed scalability, but you didn't reclaim performance. So the idea here is be chunky, not chatty. Next one, I'm going to talk about 3 different things. Minimize the size of your payloads. So the more bytes you are sending across the wire, the less performing and the less scalable you are going to be. I'm going to give you 3 examples that my teams commonly use to gain scalability. Some are easy to use. Some are harder. And we'll talk about why some of these things are that way. First one is byte shaving. So here you'll see an example of a class. It's just a sample class. And you have some properties on it, like an ID field, a sample type, and a collection of sample data. Well, if you were to do nothing, the JSON format, and actually, you know what, next time I do the slide, I'll put the JSON representation on here, but the JSON values here would be the full names. So sample type and values and ID. But you can see we are actually changing the names of these properties on this class so that when it's serialized across the wire, that it's represented with fewer bytes. So rather than the full name sample type, we replace that with just ST, right? So sample type. Instead of the full name values, we replace that with V for values. That allows us to reduce the size of the payload very quickly and easily. The only challenge with that is if you have a consumer of this, they better know what ST and V are, right? So you can accomplish that through documentation or some other thing. This is also good when you have internal APIs If you have external APIs that people are consuming, you might just bite the bullet and say, I'm not going to do this, right? Because it's more important for me to be self-explanatory in my payloads. The last one, which is a variation on this, and there's so many different techniques. I had to do something over the past year that took me to the next level of this type of stuff. Actually, Jim, you and I actually did this one here, which was the use of short GUIDs for representing GUID values. So the idea behind this is a GUID is a unique identifier. It's commonly used, especially in services like microservices, where you want to provide a globally unique identifier. It can traverse networks, it can traverse applications. So when it round trips back to you, because it's globally unique, you know exactly what thing you're looking for. But a GUID, if we were just to look at it as far as bytes, is 16 bytes. That's great. However, JSON is text. It's not bytes. So we have to take that 16 bytes and convert it into JSON. Well, the standard textual representation of a GUID is 36 bytes. So we increased the size of this GUID from 16 bytes to that long value shown on this slide. Well, because JSON is text, we say, is there an alternative representation that still meets the textual value and can represent a GUID? The answer is yes. So you can see the big long value with the dashes in it is the GUID. Right below it is the short GUID version of that same value. So we went from 36 bytes to 22 bytes. Doing what? Really nothing. It just did the same operation, but instead of saying, hey, use the long version of this, use the short version of this. There are two things to mention here. This is in .NET. To accomplish both of these goals, we use the serialization library. The latest version of this is in system.text.json, .serialization. And we use the JSON property name to shorten the name values. And we use a JSON converter to take a GUID value represented in .NET and convert it to the 22 bytes. With those two capabilities, we can actually reduce the size of our payload by not really changing what we're doing. We're just representing the bytes that we have in a shorter representation. Okay. Then there's compression. So JSON is a big text-based format, right? So most of the time when I see REST APIs, people are sending a lot of data back over using JSON over a REST service. A lot of times they send collection of things, right? So it's not one thing they're sending many things, N things. So what ends up happening is because this is text, it's almost like you're downloading a big text document. Well, kind of sucks. Why? Because you're sending all these bytes on the wire. It takes a long time to serialize those bytes on the wire. Wouldn't it be great to say, take this big JSON document, make it smaller, and send less bytes on the wire? Well, guess what? You can. Part of the HTTP standard is the ability to support response compression. Notice I said response compression. We'll get into that in a second. There are a few compression formats. The most common one is gzip. The second more interesting one is Brotli. This came out in the last few years. Google kind of, pushed it along. It is a little faster and sometimes can get better compression. But the idea here is if you're going to send 1,000 bytes, compress it and send less bytes. I can honestly say that you may get 1/10 the size of the bytes that you send on the wire. So if before you send 1,000 bytes and now you send 100 bytes and you're sending the same information, that's a good thing. There's one downside to this. In order to handle this, you have to do the compression, and that often is done dynamically. So when you get a response, it has to take that response, compress it, which uses CPU. So the expense of using this is at the cost of CPU on the server that is compressing it. And then it sends it over the wire. And then when you uncompress it, you're using more CPU on the client. Most compression algorithms are highly efficient these days, and .NET is no different. In fact, even in the latest version of .NET, they've improved the compression. But I would definitely, this is like one of the first things I do is just turn it on. So last thing, gRPC. gRPC, I haven't talked much about it, and there isn't a dedicated slide on this, so I'll talk a little bit about this right now. It's there to provide better capabilities than, say, what REST has to offer with HTTP and JSON. First, it allows you to use lower level protocols like TCP, which is great. And it also allows you to use things like binary serialization, which inherently is smaller than JSON as it is. Because of those two things, gRPC is often faster, right? It also uses a better protocol for actually a better serialization format known as Google protocol buffers. And that is more efficient than JSON significantly. However, in the case of compression, one thing I'll point out is there is out-of-the-box support to allow compression of both requests and responses. So I mentioned for this response compression, this is mainly for REST-based services. And you make a request and the responses come back as compressed. But what if you have a lot of data to send to a server? Well, you can do it. We've done it. But there's not a lot of information on the internet on how to send REST-based requests in a compressed format. You can absolutely do it. It's just not common. So, all right. Better serialization. So there are two formats of this. The first one is easy. There is a library known as Newtonsoft JSON. This has been the predominant JSON library in .NET for, oh geez, I think a decade at least. But in the last couple of years since .NET Core came out, there has been a new standard for JSON, system.text.json. Newtonsoft JSON was not built by Microsoft. It was built by James Newtonsoft King, right? You know, Newton King or something like that. And great guy. He now works for Microsoft. He now works on two interesting standards, system.text.json and gRPC. So the guy that wrote Newtonsoft JSON is now doing system.text.json, is working on Microsoft's Google remote procedure call library. That being said, so option number one is if you have services out there that is using Newtonsoft JSON, stop. Don't. Get rid of it. Move to system.text.json. There is huge enhancements with this, especially with memory, which I'll talk about in a minute. But, you know, the idea here is move forward and don't look back. Option number two is replace JSON with a different serialization format. And there are many different serialization formats. We'll see a couple in a minute. But the idea is JSON is good. It's ubiquitous, but it still is a text-based format, still has overhead. It doesn't have as much overhead as more robust text-based formats like XML, but it still isn't that binary serialization that is the smallest that you can get. Enter Google protocol buffers. The protocol buffers, they offer a better serialization format, which is one of the reasons why gRPC uses this. Here are some different types of serialization formats. JSON, protocol buffers, message pack, BSON, which is basically binary JSON, XML, and there's many, many, many more. Depending on which serialization format you pick, it will impact the reach of your services and who can consume them. JSON is ubiquitous. It's in every browser on the planet, which means it has the highest reach. As you go through these things, there has to be more effort for people to consume your services. Okay. Let's talk about one of my favorite things to do. So I'll give you an example. I work for a big online retailer right now, and they needed a service to calculate discounts on their product catalog. And when I say online retailer, I mean big online retailer. Amazon like online retailer. It's not Amazon, but big online retailer. So they have something like 130 million products. And we had to develop a microservice that said, hey, for this product, so one product, in the catalog, what are the discounts associated with it? Well, imagine if I had to do that 130 million times. And by the way, we're working on growing their product catalog to infinite scale because they are growing. So that being said, if we had to do this one request at a time, I'd be curious if somebody wants to do the math. Let's say each request took 50 milliseconds. And you took 130 million requests and times by 50 milliseconds. How many minutes, hours, days would that be? It would be a very, very, very long time. My note to self is I should put that on the slide. So, but it isn't a few days. It's something ridiculous like hundreds and hundreds of days, right? So, but one of the ideas here, and this is just a quick win, is rather than sending a request for one product, maybe you send a request for 1,000 or 10,000. And actually today we do it 10,000 at a time. And it's good because they reprice their product catalog every 2 hours. And within that 2-hour window, they're making all the calls to us and saying, what are the discounted prices for these 10,000? Now, that's not the only thing we do, but batch calls with requests are great. So we're sending 10,000 things up and we're getting 10,000 responses. This is kind of what represents, you can see here, multiple requests back and forth. But now we have a single request with multiple requests in it. That's the batch. Well, as I mentioned, the more turns on the wire, the more network calls that you do previously, you get slower, right? It reduces, and that becomes a problem. Well, by batching, we reduce the number of calls across the wire. That's a good thing. One really cool thing, though, is this is all light data. So both on the request side and the response side, we're making requests. We're saying, give me these products. Most of the time, it's a combination of IDs that we're looking for, product IDs. And on the response side, it's a collection of discounts for each product. Well, it's all light data. Light data compresses extremely well. So rather than some big response, using response compression, we send less bytes on the wire. This is where batching and response compression work really, really well together. This is like chocolate and peanut butter, two things that go well together, right? So in this case, batching and compression is a very, very good thing. Okay, I mentioned earlier about memory allocation. You and I had this problem. So I know Jim Wilcox very well. Worked with him many times. One of the challenges with JSON is when you send a list of things back, the JSON format doesn't say how many things are in that list. It just says, here's a list. And serialization libraries like Newtonsoft JSON say, oh, I've hit a list. Let me create a list object and let me start reading and populating that list. Well, depending on the implementation of that list, you may be doing a ton of memory allocations you shouldn't be doing. So there was one time when I was working on a product. Let me see if it's on the next slide. It isn't. So we were building a product to compete directly with Instagram. And at the time, it was very cool. You know, you could use your mobile app and you could take your photos and do a bunch of things. But a lot of the stuff that we were sending or requests we were sending to the server and getting responses, we were getting collections of things. So collections of pictures, collections of events. And what was happening was every time we got a list, there would be a ton of memory allocations. Here's why. There are many implementations on how you can create a list. This is a not so good one. So the list starts out with an allocation of, say, 4 items in the list. I believe that's the current implementation in .NET is 4. When you add 1 item, no allocation. You add 2 items, no allocation. Add a 3rd one, no allocation. Add a 4th one, still no allocation. Enter number 5. So here comes the allocation. We go to add the 5th thing, and there's a backing array on this list. And it says, I need to grow the array in order to add this 5th item. How does it grow it? It uses something known as a doubling algorithm. So the capacity size of the array was 4. Let me double it. I'll resize it to 8. And then I will add the 5th item. Anybody want to guess when that array is going to grow again? Anybody in the room? Yes. 9th item. I go to add the 9th item and it's growing again. And I said it was a doubling algorithm. So capacity of 8. Go to add the 9th item. The array grows to what? 16. So if you have 1,000 items to send, and the JSON library comes along and says, hey, I'm going to populate this list with 1,000 items, it's constantly growing and creating arrays and throwing those arrays out. Because what happens is it creates a new array, copies the values from the old one, populates the new one, and the old array has to get garbage collected. Well, if you have 1,000 items, you probably have like 6 or 7 allocations right there. And then if you scale and have, in our case, we had 40,000 users, right? We looked at our server and we said, oh my God, we're spending 30 to 40% of our time on our server allocating arrays. So, doctor, it hurts when I do that. Don't do that. So we fixed this problem. Again, using a custom JSON converter, we would emit the capacity in the JSON payload. And when we would deserialize the list, the first thing we would do is say, is the capacity of the list available? And if so, we would pre-allocate, avoiding any of those interim allocations of memory. There is some features. This one isn't one of them, but there is some features in system.text.json that do help with memory allocations that Newtonsoft JSON did not have. So part of this is definitely move to system.text.json, but if you want to get really good performance, you may have to go to the scale that we went to. This is not a .NET problem. This is a JSON problem. So pretty much I don't care what language you're in, whether it's Python, Java, whatnot, you're going to have this problem. So. All right. This is the client side thing that impacts server scalability and performance. In the HTTP standard, there's something known as persistent connections. It's also referred to sometimes as keep alives. The idea here is if you're using HTTP 1.0, what would happen when you wanted to make a request to a service? It would say, open an HTTP connection to a service. Response, close the connection. Next time you made a oh, what happened?
I grabbed this by the power button.
Shall I pause?
Just a split second, you're back. Sorry.
Okay, you want to get rid of oh, do you need that up?
This is the chat. Yeah.
Okay, all right. Okay, so where was I? Open the connection, make a response, make a request, get a response, close the connection. Well, if you're making multiple requests to the server, you're doing open connection, make a request, get a response, close the connection. Open a connection, make a request, get a response, close the connection. There is overhead. So one of the things that happened is they said, let's have persistent connections, the ability to pull these connections and keep them around. Browsers love this, by the way. Okay. Why did browsers love this? Well, they could say, hey, we could allow you to have multiple connections open simultaneously. So the standard, by the way, says 2 connections. Nobody follows the standard. Google was funny at this. I think Chrome does 10. But the idea is if you're in a browser and you hit a web page, it's downloading the web page. And as it's downloading it, it says, ooh, I have an image to get. I have a JavaScript file to get. I have other things to get. So when you see a browser rendering, you don't see like one thing going on at a time. You see many things happening. And this is mostly thanks to persistent connections that you're able to simultaneously make requests, and those requests are going over pool connections. And the capability now is this: open a connection, make a request, get a response, make a request, get a response, make a request, get a response. And then there are multiple connections that you can have open, right? So the standard says 2. Interestingly enough, 2 kind of sucks, right? So I'm just going to say it like it is, especially if you want to have very snappy response times. That's why Google, if you look at Chrome, they're like, I'm not doing 2, I'm doing 10. And they all do that these days. Edge and Firefox and Chrome, they all do that. But if you're building an application, same thing applies. I don't care whether you're building a mobile app that's calling REST services or a web app that's calling REST services. You still want to have more than 2 if at all possible. In .NET, if you are consuming these services and you want to make calls to either backend services or services out on the internet, and you're hosted in ASP.NET, you get 10. For all other processes, for the most part, you get 2. That is the default. You can see here, though, I have a little piece of code that I always put in my server-based applications, which is I'm not limiting myself to 2 or 10. I'm going to go to 100 or 200. Why? I had mentioned that a lot of modern applications are built consuming many microservices. And the front ends to those applications are many users. The last thing I want is to be saying, I support 40,000 users and I'm gated by 10 connections, right? I don't want to be limited by 10 connections. So we often turn this up. So think of this as a limiter, and I'm just taking the safety rails off and saying, hey, we're going for it. Along with that is a very similar thing. By the way, that last slide and this slide are new to this deck, and I should have had these in a long time ago, but I didn't. but this one is about reusing HTTP clients. So on a server, there are only so many connections to the server that can be made. And if you have many, 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 many clients, the hope here is that you are pulling your connections on the client rather than a client saying, I'm going to open up 100 connections. I'm going to pull them in some way, shape, or form so that I can reuse them if they're not being used, meaning they're not currently in a call to the server. The reason for this is you can have socket exhaustion. What that means is all the sockets on the server are taken up, and I can no longer accept any new connections for users. The way around that is to scale out. But again, every time I scale out, it costs me more money. So in this case, there are a couple of benefits. One benefit is I'm more efficiently using the resources that I have. And on top of that, I'm reusing things and therefore not having to allocate a socket and all the other stuff. And therefore I get better performance with less connections. There is a recommendation on how to use the HTTP client. The latest standard is to use either a static or a singleton instance of the HTTP client. That will put you in the situation where you are getting this capability. There is one downside, is DNS may change. So imagine you have a data center failover. You're communicating to, say, Azure on the East Coast. Data center goes out. Oops, I now need to switch to the West Coast. Well, if your DNS entries change regularly, you're going to want to set the pooled connection lifetime to something appropriate so that when it goes into a retry state, you eventually switch to the other location. This one is one that's extreme. How many of you are comp sci majors in here? Raise your hand. Anybody? All right, that guy over there. All right, any engineers? Engineer? Okay. All right. So my degree is in electrical and computer engineering, and I was always the geek that was in the computer lab, sitting on some computer when I was like real little. So my mom used to drag me to her college classes and stick me in front of the computer. I did not have a formal comp sci education. My education with computer science is all by doing myself. This is the one area where I wish I'd taken a few classes in computer science, specifically around data structures. There is one data structure that took me a while to learn what the heck it was, but it's so darn cool. So most people are familiar with dictionaries, right? A dictionary is, hey, I am looking for something. Let me look to see if the value is in the dictionary. So I give it a key and the dictionary says, yes, it's in there, or no, it's not. Bloom filters don't do that. Bloom filters basically say, take the key. Is it in my list or collection associated with the Bloom filter? Keywords associated with the Bloom filter. And the answer is either no or maybe. And I say no is the most important thing. A Bloom filter is very compact. So it is a data structure that can fit in a very small size. One of the things it offers is if I have a list of things like 130 million products and whether those products have discounts or not, and let's just say 10% of the catalog had discounts, that would mean 117 million things did not have discounts. Right? That's interesting. Well, it also means 13 million things have discounts. Well, remember I said we're making calls across the wire? Well, a Bloom filter being compact in size associated with our dictionary that has the discounts for all those products, the Bloom filter could say, does a discount exist for this product? Yes or no? And it's actually not yes or no, it's no or maybe. And if the answer is no, that's the best response we can get. The answer is maybe, we'll talk about that in a second. So I also said Bloom filters are compact in size, which means we can send them over to the wire to the person that's interested in knowing, are there discounts in our service? So the person that's consuming our service, first thing that they do is they say, hey, is there a discount for this product? And they don't make a service call to find out. They ask the Bloom filter, is there a discount for this product? And if the answer is no, it does nothing. It says, thank you very much. I already have my answer. If the answer is maybe, it makes a service call and the service says, yes, I either have one or no, I don't. It is a probabilistic data structure. But because the Bloom filter could say very easily, nope, I don't have anything, we eliminate 117 million network calls. Okay, that's pretty darn cool. This technique is widely used at Google in their microservice implementations. It is one of the more advanced techniques, and it is just awesome. So, okay, protocols. So far we've been talking REST and gRPC. Each one of those things, for the most part, uses some variation of HTTP or TCP. But there are other protocols out there, things like, hey, WebSockets. So WebSockets are an interesting thing. They allow for bidirectional communication between client and server. It does bootstrap using HTTP, but once it's negotiated that WebSockets are capable, it sheds that HTTP and drops down to TCP, which inherently has bidirectional capabilities. We could just say use TCP, right? And gRPC does a lot of that. So, just using, the lower level protocol, which HTTP is based on, that is an option. Then there's multiple variations of HTTP. So I had already mentioned HTTP 1.0. And by the way, persistent connections that I spoke about earlier were introduced initially in HTTP 1.1 and have been improved in HTTP 2.0. And there's a new one called HTTP 3, which I'll talk about on the next slide. There are other protocols as well. MQTT is a very common protocol used in IoT-based applications and satellite communication. UDP, this one is very cool. It is kind of the lower level, one of the lower level protocols like TCP. I've mostly seen this used in gaming, right? So most gaming companies, they love to use UDP as their network protocol for game instances of gamers communicating with each other. So one final point on this is they are working on an abstraction in gRPC so that you can use many different types of protocols, not just the ones that come out of the box with gRPC, like TCP and HTTP. HTTP 3. All right, this is supported in .NET 7. It was sort of available in .NET 6, so keep that in mind. It is based on a standard known as QUIC, QUIC. This is, again, another contribution from our friends at Google. It is based on UDP, not TCP. Because it's based on UDP, it does offer some really cool features. One of the features that I'm more interested in, and I'm kind of just bummed about it and just hoping Microsoft will get this out there, is the seamless transition between networks. So if you're using a mobile phone and you're communicating to services, you're often roaming. So if I walk down the hall, I might be hitting different routers. I might transition from cellular to Wi-Fi and back again. But during those transitions, what I don't want is error. So if I get an error, I have to go and retry. Well, using HTTP3, there is the ability to handle those things and handle that negotiation and handle that connectivity below your application. It's done for you. So as you transition between networks, this seamlessly will, just switch the connection and fulfill the requests. Here's another feature, and here is that in HTTP2, when you are multiplexing multiple requests via a single connection, if you have a packet loss, it affects every single request. Well, that's kind of sucks. Even those requests that don't have a packet loss, this affects. Well, with Quick and HTTP3, it supports native multiplexing, and therefore, when a single request has a packet loss, it does not affect everybody else. Okay. The one final thing is that because this is based on UDP and some of the other underlying technologies, negotiation of connections are much faster. And because the negotiation of a connection is faster, the first request reaches the server more quickly, and therefore you get a response more quickly. So these are kind of the three big things. You can do this right now with HTTP client and Kestrel, which is the .NET server in .NET 7. However, the seamless transition is not currently supported, which is kind of a bummer. So the first two things here work. The third thing, I'm sure it's on their roadmap. When they'll get to it, who knows? One final thing about HTTP3. You have many things that you might transition through across the network. Things like routers, API gateways, and things like that. Depending on what you're doing, you may not be able to use HTTP3. It really depends on, the proxies and firewalls and routers and stuff that you're using. But for the most part, attempt to use this. Hopefully, more than likely, you'll be able to use it. Just know that depending on your scenario, you may not be able to use it just yet. All right. That's what's missing. Interesting. Okay. I had somebody modifying my deck, and I was like, where is this one slide? Okay. They merged this one slide, I think. All right. There are two things I wanted to talk about. I'll talk about both. So there should be 11 lessons in here. This should be a lesson 11. .NET 7 is the fastest .NET ever. It literally is fast. They've made improvements in the microservices for things like compression, JSON, networking, collections. The list is long. And when I say this is the fastest .NET ever, it's not a little bit faster. It's a lot faster. So if you're currently doing .NET today, upgrade. You're going to benefit from it. If you're currently on .NET 6, it's an easy transition forward. If you're on an older version of .NET, it might be a little bit more difficult, but it is the fastest way you can get with performance. Now, I have mentioned, why did I put this slide up here? This seems like kind of like an easy, upgrade and get performance. Well, microservices I mentioned previously, as soon as you break apart that monolithic application, you are impacting your performance. And I can tell you, we spend a lot of time reclaiming that performance back. And anything like this is godsend, right? So, I just upgrade and it's all good. There was supposed to be another slide, and I'll just talk to it because the graphic is on this slide. And it talks about API gateways. So an API gateway is a great way to aggregate multiple services together. So if you have a whole bunch of teams working on separate services and you need to create a collection of these things to represent your application and its needs, an API gateway is an awesome way to do this. Some things that API gateways provide that, having many services behind the scenes might be difficult is things like common security, maybe across all those services. So say different teams decided to do different things related to security. You're an application builder. You want to have one thing to rule them all, right? Well, an API gateway can handle that, but it can also handle things like load balancing. It can also handle things like SSL, TLS offloading. So that's the encryption for HTTPS, right? So API gateways are definitely a very cool thing. Okay. That was my 10 or 11 lessons on advanced microservices. I do have a couple, kind of references here. There are references throughout this deck. I'll make sure that this is available online. We do have a proof of concept that we did on gRPC versus REST. And interestingly enough, if you do all the things I say in this deck, you'll come darn close to what gRPC offers for performance. Now, REST is HTTP plus JSON. It is ubiquitous, highest reach you can get. So if your desire is to have many people consuming your API, go with REST. If your desire is to have the best performance and you don't care about, tons of people reaching your API or microservice, and you have a limited set, go with gRPC. Both are great. Along the way, and interestingly enough, in preparation for this, there was a great microservices with .NET. It is based on .NET 6. This is both an online article and an online book. It was published by Microsoft, and it came out, what's today, the 12th? Came out on the 8th. I was like, oh, well, this is a really great book, so I put it up there. And then there's some guidance here on using HTTP3 with HTTP client.